Welcome to Hartman Math. This is lesson 7.3, multivariable linear systems. So we're going to be solving maybe larger equations, maybe 3 equations, 3 variables. You've probably already done that before. We're going to take a look at it from a slightly different perspective and algorithm, and then maybe later we'll explain why we're exactly doing this. We're going to start with kind of a basic one, example number 1. We have a 3 equation, 3 variable system. We want to solve this using back substitution, meaning since we already have the value for z, let's plug that back in somewhere that allow us to find either x or y and so on. And in the end, we're going to want to write our answer as an ordered triple, something, comma, something, comma, something inside of the parentheses. Since we know what z is, since this one only requires y and z, if we replace this z with 1, we'll be able to solve for y. So y is going to be negative 1. Now we know z and y, we can go back into the first equation, replace y, replace z, and solve for x. Add 7 to both sides. There we go. So our ordered triple is 5, comma, negative 1, comma, 1. We go in alphabetical order. And that's solving using back substitution. Now we're going to take a look at in a second is that this system is in what's known as row echelon form, where the first equation starts with 1x, the second equation does not have an x, it starts with 1y, and the third equation starts with 1z. So we're going to use as a way of solving. It's definitely not the simplest or the most efficient, but there's a reason for it, and it's very algorithmic. So we're going to solve by Gaussian elimination. Here are the 3 things that we're essentially allowed to do within Gaussian elimination. We can take any 2 equations and switch places. We can multiply one of the equations by a non-zero constant. Say, I would like to multiply the second equation, everything through by 5. That's legal by row operation number 2. Or I want to multiply everything by 1/2. That's legal by number 2. And then third, I can add a multiple of one of the equations to another equation to replace the latter equation. So I can say I would like to multiply the first equation by 3 and add it to the third equation. That's allowed. Now what's not allowed, because it's not one of these 3, is I would like to multiply this equation by 2 and that equation by 7 and add them together. That's not allowed by one of our operations. We could do them in separate steps. I could multiply an equation by 2 and another equation by 7. And then later I could just add them together in separate steps, but not together. Our goal is row echelon form for our system, the one that we just saw in example number 1. First equation starts with x. Second equation starts with y. Third equation starts with z. How it has that stair-step look to it. That's row echelon form. So let's go ahead and copy down example number 3. It doesn't work out so well here in terms of slides, so I'm going to start writing this down on binder paper. Go ahead and copy this down first, and then we'll go ahead and look at it on some binder paper. So pause here until you're ready, and then we'll hit resume. Okay, goal number 1, we want the first equation to start with x. It already does, so that part is taken care of. Now what we'd like to do is underneath that, eliminate the x's that are below that. So equation number 1 is good as is, so we're going to rewrite that. And every time we rewrite, we're rewriting or changing all 3 equations. So now, here, with these 2, I can add these 2 together to eliminate the x's. And I'm doing row operation number 3. I'm essentially multiplying the top equation by 1 and adding it to row 2. So by doing that, I'm going to add them together. I get 0 x's. I get 1y. 3z is equal to positive 2. And to remind myself what I did is I added row 1 to row 2. Now I want to do something similar and eliminate the 2x also. And I need to do the same operation. So within one step here, here's one step. I can't do two different row operations, but I think I can do the same row operation, which is row operation 3. I want to multiply this by negative 2 and add to that, because then I'll have negative 2x plus 2x is gone. So I'm going to multiply the top equation by negative 2 and add it to the bottom one. So if I do that with the y's, I get negative y. And if I do it to the z's, I'm going to get 8z minus 6z is positive 2z. And positive 4 plus negative 1 is 3. So again, as a reminder, I multiplied row 1 by negative 2 and added it to row 3. And that created a new row 3. All right, so x's are taken care of. We got the first one to start with x, and x is eliminated below that. Now we move on to the y's. The second equation needs to start with y. Yay, it already does. And then we need to eliminate the y below it. So the first equation is fine. We'll rewrite it. The second equation starts with y, so it's fine. We'll rewrite it. Now the third equation, we want to eliminate the y below it. So let's just add row 2 to row 3. 0y's, 5z is equal to 5. Again, we're doing row operation number 3. We added row 2 to row 3. Now, we're very close, but we're not quite there because our last equation needs to start with z, and right now it starts with 5z. So we need to have to get rid of that 5 somehow. But the other two equations are good. Now we need to rewrite the entire system. Or the ones that are okay. Row 1 and row 2 were okay. We rewrite them. Now, for the last one, to get rid of that 5, we could do row operation number 2. We could multiply both sides by 1/5. So z is equal to 1. We did 1/5 times row 3. And now it's in row echelon form. And I think this is the exact same one that we just solved in example 1. So by going through the back substitution, we could arrive at the solution 5, comma negative 1, comma 1. There we go. Now let's do another one that maybe doesn't work out so nicely. Here's example 3 plus. You might want to pause here to get it all written down. Remember, we want to have the first equation be just x at the start. And there's a couple ways we could do it. We could take the first equation and multiply everything by 1/2. That's definitely legal, but we would create fractions here and there. And not that that would be impossible, it just adds a little bit of a level of difficulty. Sometimes one of the other equations might just start with x, and then we could do operation number 1. We could start by just switching them. We still have to write it correctly first, and then the next set we could just say, hey, I switched row 1 and row 3 if row 3 had started with a 1x. But here's another option. We can do row operation number 2. I'm thinking if we look at these two, if I multiply the first equation by negative 2 and add it to the one underneath it, row 2, I would get negative 4x plus 5x is 1x. So that's what I'm going to do. I'm going to multiply the top equation by negative 2 and add it to the second equation. And our new first equation is x. There are 0 y's, they canceled out. And then negative 6z plus 1z is negative 5z. And then 5 times negative 2 is negative 10. Plus the 17 is 7. And then that's going to be it for this first try, is we just got the first equation to start with x. So I'm just going to rewrite the other equations. Next thing I want to do is eliminate the x's below it. So this is going to be like the last one, where I want to multiply the first one by something, add it to the second one. So I think what's going to work here is if we multiply negative 5 by row 1 and add it to row 2, put that in the wrong spot, because the first one we're just going to keep it because we like it, starting with x. And we're going to multiply by negative 5 and add, so gone. Multiply by negative 5 and add, we get 2y. Multiply by negative 5 and add, we're going to get 26z. And multiply by negative 5 and add, we're going to get negative 18. And then do something similar. We want to eliminate this one, again using the first equation. So negative 4 times row 1 plus row 3. Multiply by negative 4, gone. Multiply by negative 4 and add. So we're going to get y. Multiply by negative 4 and add, plus 21z. Multiply by negative 4 and add negative 17. All right, so now we need to, our next step is we need to work on that second equation. It needs to start with y. We've got a couple pretty basic options. Since I like the first equation, I'm just going to rewrite it. It starts with x. That's what I want. And now there's a couple things we could do. We could easily multiply the second equation by a half. Not a problem. Or we could just switch these two. So y plus 21z is equal to negative 17. 2y plus 26z is equal to negative 18. And what did we do? We switched. I'll throw a c in there. Switched row 2 and row 3. And now we would like to eliminate the 2y that's below the y. So we'll keep the first equation, starts with x, we like it. Keep the second equation, starts with y, we like it. And now we need to multiply the y by negative 2. So that's row 2. Add it to row 3. So multiply by negative 2 and add, gone. Multiply by negative 2 and add, we're going to get negative 16z. Multiply by negative 2 and add to the negative 18, we're going to get 16. Again, we're going to need to go another full step. So keep the first equation, starts with x. Keep the second one, starts with y. And now with the z's, pretty easy. We can just multiply both sides by negative 1/16. Z is equal to negative 1. And our system is now in row echelon form, and we can solve that by back substitution. We already know what z is, so let's replace this z with negative 1. We get y minus 21 is equal to negative 17. So if we add 21, y is going to equal 4. And then if we go into the top one, x, and then replace the z with negative 1, so negative 5 times negative 1 is positive 5. So x is 2. And so our solution is now 2, 4, z was -1. There's the solution. All right, let's take a look at example number 5, whereas it says we might end up with a system that has infinitely many solutions. So here's our start. Remember, our goal is to get row echelon form. So our first one starts with x. We're good. The second one starts with y. We're good there. We do need to eliminate this x right away. That's going to be our first goal. So let's multiply. Well, actually, I don't think we need to multiply. Let's just add these two equations. That'll create a new third equation by adding these. X is gone. 3y minus 6z is equal to 3. And now, second one starts with y. We're good there. It was a little premature before trying to look at the y's. Had to take care of the x's first. So now this one's good. Let's eliminate here. So row operation number 3 says we can multiply this one by -3 and add it to row 3. That creates a new row 3. So if I do that, y's are gone. Hey, z's are gone. So really that creates the number 0 plus 0 is equal to 0. So that's true. If it was not true, let's say we got 0 equals 5. I think that's a no solution case, but this is true. And it's an equation that doesn't have any variables. So essentially we have three variables, but 2 equations, because this one doesn't really count. And any time that we have more variables than equations, we're going to have infinitely many solutions. But unlike in previous courses, we're not just going to stop there. These infinitely many solutions are not just random solutions. They occur in patterns. We're going to go after and look for those patterns. So what we're going to do is in the smaller one, we're going to solve for y. So we got y is equal to 2z plus 1. And then we can substitute that back into the first equation. Replace the y with 2z plus 1. Distribute, simplify. So x is going to be z plus 2. So we solve for y in terms of z. Plug that in, we were able to solve for x in terms of z. So we now have everything in terms of z. So what we do is we're going to set z equal to some other arbitrary variable that's not necessarily connected to our system. A could be a good choice. It doesn't have to be. It could be S. It could be K. A is a very popular choice here. So we're going to say that z is going to be A. In which case, y would be 2 times A plus 1, and x would be A plus 2. So our ordered triple is A plus 2, comma 2A plus 1, comma A. So let's just see, yeah, it's infinitely many solutions. What are these solutions going to look like? Well, let's pick a value for A. Let's say A is 1. Then 3, comma 1 is a solution. What about A is 10? 12, comma 21, comma 10 is a solution. It doesn't mean that every combination is a solution. What about 0, comma 0, comma 0? Well, if we plug those in, you're not going to get 4. So that's not a solution. Infinitely many solutions doesn't mean that every combination of numbers is. But this is the pattern that is the solution to the system that we were looking at. One other thing, how about A is 100? 102, comma 201, comma 100. That's a solution. Example 8, data analysis curve fitting. We've got a parabola written in polynomial form, and the points go through, these points are on the graph of the parabola. What's going to happen is each of these points is going to generate an equation. Y x. So we're going to replace x with negative 1. When we do that, this is our equation. Y is 1, x is 0. Y is negative 8, x is 3. 3 squared is 9. 9 times a plus 3 times b plus c. So here's a solution. Doesn't say that we have to use Gaussian elimination, so we can just do regular system solving. A little back substitution, we've got c is equal to 1, so if we make that equal to 1 and that equal to 1, these two equations can become a 2 by 2 system. And we can solve that one. If we're just using the elimination method, maybe I would multiply this equation by 3, so then I can add them together, cancel out the b's. So a is going to be negative 2. We already know that c is 1. We can substitute negative 2 back into one of these. I kind of like that one right there. B is 3. So our equation, y equals negative 2x squared plus 3 times x plus 1. There's the equation of our parabola in polynomial form. That's it for today. I'll see you next time.